Hi, welcome back. Today we're going to be taking a look at the first derivative test. This is a test that allows us to determine whether or not a function is increasing or decreasing. And when we talk about a function increasing and decreasing, we're going to be looking at their rates of change, or their slopes. If a function is increasing, we say the function will have a positive slope. It's going to be moving upwards. If it's decreasing, we say the function has a negative slope because it's going down. So if we were to look at this graph right here, I can easily say where the function is increasing. It's increasing between 0 and 1, and I can write that down, 0 to 1. And there's more places. I can say it's increasing from 3 to 5. And we're going to justify this, and this is because we can say that the slope is positive. Now we're going to make this look much more nerdy later on, but right now that's okay to write. Where is this decreasing? Well, I can say it starts decreasing at 1 and it ends at 3. So I can say it's decreasing from 1 to 3 or from 5 to 6, where the slope is negative. I want a negative slope. Using your tangent line of mathematics, your pencil, you can see that. So we can say this is decreasing on 5 to 6, and that is because, again, the slope is, in this case, negative. So how do we test for an increasing or decreasing function? And that's our little rules today. Well, we say a function is increasing on a domain if the slope is positive. So now we are going to nerd it up. Well, we don't want to say the slope in calculus, so what we say is that the derivative of the function is greater than 0. That's what we're going to write. Because what does the derivative find but the slope? A function is decreasing if the slope is negative. Again, we're going to nerd this up a little bit by saying that the derivative is less than 0. And we're going to say, and then the last one, a function is constant if there's no change in the slope. If the slope is 0 or where the derivative is 0. You might remember we call these critical numbers. So if we take a look at these critical numbers, so we can look at the critical numbers up here. If we notice, here the slope is 0, and over here we said the slope was 0, and here I know the slope is 0. So now we're starting to see why we call these critical numbers. These are points on the interior of the graph where the function could be changing direction. And we talked a little bit about that yesterday, that critical numbers are on the interior of our function. And it's at the interior where the function is going from a positive slope to a negative slope. So finding these critical numbers does become very important for us later on today. So let's take a look at the first function here. We want to determine if this function is increasing, decreasing, or constant at x equals negative 2. So I have to take the derivative. Taking the first derivative, we get 3x squared minus 3x. If we were to plug in negative 2 into our derivative, this becomes 3 times 4 minus 3 times a negative 2, and that's 12 minus 6, which is going to be greater than 0. So what this is saying is that we have a positive slope. And our rule says if we have a positive slope, we know the function is increasing. So we can say at x equals negative 2, f of x is increasing. We know that because, and we're going to nerd this up, we're not going to say the slope is positive, we're going to say our derivative is greater than 0. It means exactly the same thing, but it sounds much more smart to say it that way. This leads us to what we call the first derivative test. And what the first derivative test says is if a derivative is less than 0, we say the function is decreasing. So if our slope is negative, we're going down like a disco clown. If the first derivative is positive at a point, we say the function is increasing. We're going up like a disco duck. Now, there's two more things it tells us. let's say the derivative is changing signs. Let's say the derivative goes from positive, increasing, to a negative, decreasing. Well, that means we are going up and then we're going down. In that case, this point right here is what we call a relative maximum. And we saw those the other day. Remember, when we talk about relative maximums and relative minimum, we said we had to change direction. And that's what the relatives were. We're changing from a positive slope to a negative slope. We're changing the direction of our function. If the derivative goes from negative or decreasing to positive, increasing, then we're going down and then up. At this point, we have what's called a relative minimum because we're going down and then up. So this is what we call the first derivative test. All it does, it says, if we apply the slopes of the graph, given the slopes of the graph, we can tell if a function is decreasing, increasing, if we have a relative maximum, or if we have a relative minimum. Remember a maximum? Remember for a maximum, our slope goes from a positive slope to a negative slope. For a minimum, we go from a negative slope to a positive slope. And that's how we define these. So let's look at the graph below here to kind of get us a better idea. This image will give us an idea. So let's say we're given the following two critical numbers on the interior of our graph. Remember, we are on the interior. We're not looking at the endpoints right now, just the interior of the function. So if we look at the interior, here I have a critical number, and here I have a critical number. But look what's happening. Before my maximum, the function is increasing. So we would say that the derivative is greater than 0. After we reach our maximum point, up here, this is our critical number. This is where the derivative is 0. We go to decreasing, where the slope is less than 0. So we have a maximum. Now we do have another point for a critical number. It could be D and E2. We'll see one of those today. Over here, notice the function is decreasing, but then we go to a positive derivative, to a positive slope. Sorry, that's kind of messy. Where the derivative is positive. And down here we have a minimum. And again, down here we have a critical number, where the slope is 0, or it could be D and E. It could be a cusp or corner. So it's really easy to tell. From looking at a graph, we can tell where we have a maximum min. If we're going up and then down, it's a maximum. If we go down and then up, it's a minimum. But how can we do this from a function that we can't graph? To do this, we use what we call sign charts. A sign chart is a tool that we use to help determine where a function is increasing or decreasing. Let's look at the following graph to help us draw a sign chart, and then we can answer the following questions. First, to set up the sign chart, we are going to find the critical numbers. Where does the derivative equal 0 or D and E? And from this graph, I can see it looks to be about 0 and maybe 3. From here, I am going to draw a number line. On the interior, I put my critical numbers, and I look to see if I have any endpoint. And it looks like I have an endpoint at -3 and 6. On top, I'm going to put the sign of my derivative. On the bottom, I'm going to see, well, how does that make my function look? So I think, between -3 and 0, what can you tell me about the slope? Well, it's going down. So I know that the sign of my derivative is going to be negative, which tells me the function has to be going down, which is obvious in our graph right here, but you're going to see why we do this in just a few moments, so just bear with it. Between 0 and 3, we know that the slope is positive, so it's going to go up. And then between 3 and 6, the slope is negative again, so this is going to go down, like a disco clown. Now, we want to know where the function is increasing or decreasing, so now we can answer this. We can say that the function f of x, please say f of x, is increasing on the domain 0 to 3. I'm going up on 0 to 3, and the reason why, we're going to say our derivative is greater than 0. Where is this decreasing? F of x is decreasing on two domains, -3 to 0 or 3 to 6. And that is because the derivative is less than 0. And there's our answers. So you go ahead and try this one. Remember to find the critical numbers. So to get our critical numbers, we want to find out where is the derivative 0 or D and E. That's not that bad to do. It looks to be 0 at A and B, but also at 0 because I have a vertical asymptote. The slope just does not even exist there. So next I'm going to do my sign chart. Now notice, this one doesn't seem to have any endpoints. So we're going to look at A, B, and 0 in the middle. Now, because 0 is an asymptote, I'm just going to write this as an asymptote right there. There's my vertical asymptote right here. And now I can answer my question. If I look at the slope before A, the slope looks positive. It's going up. Between A and 0, it's negative. It's going down. Between 0 and B, it's negative because it's going down. And after B, it's a positive slope, so it's going up. I can answer my question now. Where is this increasing? We can say f of x is increasing on the domain -infinity to A or from B to infinity, and that is because the derivative is positive. Where is this decreasing? F of x is decreasing, spell it out, on the domain A to 0 or 0 to B. Notice we have to put a split here because at 0 something is happening. There's no value there, so I don't want to put a point there, so I split it. And that is because the derivative is less than 0. All right, go on to part B. We'll take a look at a few more examples, more algebraic type. I'll see you then.